Hello viewers, in the previous lecture we studied about the synthesis and synthetic utility of ethyl acetoacetate, but today we will study the new aspect of ethyl acetoacetate, that is tautomerism. So now in today's lecture we will study tautomerism, reactions supporting the keto form, reaction supporting enol form, evidences for existence of dynamic equilibrium, isolation of tautomeric forms, composition of keto-enol tautomeric mixture and its determination, factors affecting relative amount of keto and enol forms in keto-enol tautomerism, acid-base catalysis in keto-enol tautomerism. Now, let us start. What is tautomerism? Tautomerism may be defined as the phenomenon in which isomeric compounds which have different structures exist in dynamic equilibrium with each other. It is a special kind of functional isomerism which arises due to 1,3 migration of one polyvalent atom to other within same molecule. It is also called prototropy. The two isomers thus obtained are called tautomers and differ both in the position of a pair of electrons and as well as a proton. Now let us see from this structure how keto-enol tautomerism exists. In this structure we label this different atom oxygen as one heteroatom and adjacent atom carbon as 2 and 3. Now in these 3 atoms the electrons shift from oxygen to this bond 2 3 and from the third atom polyvalent atom carbon proton shift to this first oxygen and it forms another form known as enol form, and these two forms they remain in dynamic equilibrium with each other. These two structures differ from each other position of electrons and the proton. So this isomerism is also known as the prototropy. Now keto-enol tautomerism, it is exhibited by the carbonyl compounds which are having a reactive methylene group or methine group adjacent to carbonyl group, and ethyl acetoacetate is a perfect example of keto-enol tautomerism. In this keto form, this methylene group it is flanked on both sides by the carbonyl group, and this H it can shift to this oxygen and electron will migrate at this position. So, and it will produce this enolic form, double bond here, and this position is the H. Now in this structure we can see that this OH, this H is bonded to the another O and form the hydrogen bond. In a similar way, this H can also be shifted to this oxygen. So it produces this structure enolic form, and these two are the enolic form, and these enolic forms they are in equilibrium with the keto form. Reactions support that ethyl acetoacetate contains keto group, that is when it was treated with sodium bisulfite it formed sodium bisulfite addition compound, and upon treatment with HCN it formed cyanohydrin, and with hydroxylamine formed oxime, and upon treatment with phenylhydrazine it formed phenylhydrazone. All these reactions shows that ethyl acetoacetate contains carbonyl group. At the same time, it also shows that it contains enolic group, because when it was treated with sodium metal, ethyl acetoacetate liberated hydrogen, which indicate that it contains enol. Again, when it was treated with PCl5, it formed ethyl beta chlorocrotonate, and it also discharged the color of bromine which shows that it contains unsaturation. In a similar way, when it was treated with ferric chloride, it showed change in color and the color was reddish violet color like phenols. And upon treatment with acetyl chloride, it formed acetyl derivative. All these reactions were reactions of phenols or enols. That shows that ethyl acetoacetate also exists in another form, that is enolic form. Now evidences prove that keto and enol forms, they are simultaneously present in the mixture. The fact that with any particular reagent, ethyl acetoacetate reacts as a whole either in the keto form or in the enol form suggests that there exists a dynamic equilibrium between the two forms. Thus, when a reagent such as hydroxylamine reacts with keto form, the whole of the keto form reacts with the hydroxylamine and it forms a oxime. So, when this equilibrium is disturbed, the whole of enol form gets converted into the keto forms, and when it is treated with the bromine water, the whole of the bromine reacts with the enol form and this equilibrium is disturbed till the whole of keto forms gets converted into the enol forms. And it appears that if it is consisted of only enolic form. So, these reactions shows that keto form and enol form, they are in the dynamic equilibrium with each other. That is, if we disturb the equilibrium, if we perform the reactions of keto form, the whole of enolic form gets converted into the keto form, and if we perform the reactions of enolic form, whole of keto form gets converted into enolic form. This shows that these two forms, they show dynamic equilibrium. Ethyl acetoacetate exists in two forms, keto form and enol form. That has been proved beyond doubt, and they remain in equilibrium. But these were isolated only in 1911 by Knorr. He cooled a solution of ethyl acetoacetate in petroleum ether to 195 Kelvin. When he got a crystalline substance which was having the melting point 234, it was obtained, and that substance did not dechlorize the solution of bromine, nor it gave the red coloration with ferric chloride. Naturally, this substance was a pure keto form. In a similar way, he got success in isolating the enol form by cooling a suspension of ethyl acetoacetate in petroleum ether to the same temperature 195 Kelvin and passing just enough hydrogen chloride to decompose the sodium salt. The resulting mixture was freed from sodium chloride by filtration and the filtrate was evaporated under reduced pressure at 195 Kelvin. This gave the oily form, and this oily substance gave intense red coloration with ferric chloride and instantaneously dechlorized an ethanolic solution of bromine. Obviously, this form was the enolic form. So, at 195 Kelvin, each of the two forms is quite stable and they can be kept in pure state for a long time in the complete absence of acids and bases. But these forms could not be stored in glass because the glass contains traces of alkali metal which catalyze the conversion of one form into another form. So, quartz vessels were used for this purpose and the two forms were stored in quartz vessels, but on standing at the room temperature for some time, each form again get converted into the equilibrium mixture. That confirms the existence of dynamic equilibrium between the keto form and the enol form. Now, how we could get the pure sample of keto form and enol forms? The mere scientist, he placed the equilibrium mixture in quartz flask and subjected it to fractional distillation under reduced pressure. When enol form, being more volatile, distills first, leaving behind keto form. This type of distillation, which is carried out in the absence of dust, moisture, is called aseptic distillation. Pure samples of keto and enols were isolated. Now, we will find out the composition of keto and enol by different methods. The first method is chemical method. Mayer observed that enol form of ethyl acetoacetate, when it reacts with bromine, this reaction takes place instantaneously, and the interconversion of keto form to enol form was very slow. So, he did rapid titration by taking unknown weight of ethyl acetoacetate is rapidly titrated with slight excess of bromine at 273 Kelvin. When the end point is reached, that is, when the color of bromine is no longer discharged rapidly, an ethanolic solution of 2-naphthol is added to remove the excess of bromine. That is, bromine, it reacts with 2-naphthol and it forms this product. The reaction mixture is then acidified with HCl and Ki is added in excess. Ki and HCl produce Hi, and with Ki, the bromoester was converted into iodoester, and this iodoester, when it is treated with Hi, it liberates iodine. The iodine thus liberated is titrated against the standard solution of sodium thiosulfate. From the amount of iodine thus liberated, the amount of bromoester is estimated, and from the amount of bromoester used, the percentage of enol content in the equilibrium mixture can be determined. In this way, it was found that at room temperature, equilibrium mixture of ethyl acetoacetate contains 7.5% of the enol form and 92.5% of the keto form. Another method which was used for finding the percentage was PMR spectroscopy. The spectrum of ethyl acetoacetate gives two separate signals for CH2 and double bond CH protons. Similarly, the singlet due to CH3 protons of keto forms absorb at lower field than the singlet due to the CH3 proton of enol form, because in the keto form CH3 is attached with the electron withdrawing group. So, that CH3 gives a singlet at the lower value as compared to this CH3 which is attached with the double bond. By comparing the areas under the absorption peaks of keto and enol forms in the PMR spectrum, the percentage of keto and enol forms in the tauto mixture can be calculated. So, by these methods we could find out the percentage of keto and enol forms. Now, let us see the factors which affect the relative amount of keto and enol forms in keto-enol tautomerism. That is, this depends upon the stability of enol forms. Generally, the keto form is more stable than the enol form due to greater strength of carbon-oxygen double bond. Its energy is 364 kilojoules per mole as compared to carbon-carbon double bond. The energy of double bond is 251 kilojoules per mole. As a result, in simple aldehyde and ketones such as acetone, cyclohexanone, the amount of enol content is negligibly small, that is, even it is less than 1%. But the enolic form is stabilized by the two factors: conjugation of ethylenic double bond with the second carbonyl group, which forms intramolecular hydrogen bonds, and the formation of intramolecular hydrogen bonds, chelation between the enolic hydroxyl group and the second carbonyl group. These two factors, one conjugation, another formation of intramolecular hydrogen bond. Intramolecular hydrogen bond means within the same molecule, this OH is attracted towards the negative part of this carbonyl group and it forms intramolecular hydrogen bond, which stabilize this enol form more. That is, it forms this chelate. Chelate means ring-like structure. So, conjugation as well as intramolecular hydrogen bond both are responsible for the stability of this enolic form. And since two forms, these both factors are operating in ethyl acetoacetate, so the percentage of enol is increased to 7.5% and the keto form is 92.5%. Now let us see the keto-enol tautomerism in acetyl acetone. In this example, the keto form is 22% and enol form is 78%. The amount of enol content is much higher than keto in acetoacetic ester, since the keto group is much better electron withdrawing group than the ester group, because in ethyl acetoacetate on this side was the ester group and in this case both these groups are keto group, and it has changed the percentage because of better conjugation, better formation of intramolecular hydrogen bonding. The percentage is increased to 78%. Hence, higher stability of enol form implies greater enol content. The solvent also plays an important role in determining the percentage of keto and enol. Now, any solvent that can form hydrogen bond with carbonyl group will stabilize the keto form relative to the enol form, because enol cannot form hydrogen bond with the solvent since it is already involved in the intramolecular hydrogen bonding, as a result of which equilibrium shifts in the favor of keto form and hence the enolic content will increase. So, in general, polar protic solvents such as water, methanol, ethanol, acetic acid, which tends to stabilize the keto form relative to enol form, will reduce the enol content. On the other hand, non-polar solvents such as hexane, benzene, which do not form hydrogen bonds, tend to decrease the enol content. Now, let us see the role of acid and base in the catalyzation of conversion of one form into the another form. Let us see the role of acid in the catalyzation of keto form and enolic form to an equilibrium form. The acid H ion, these protonate oxygen when we take the keto form and they change into this intermediate, and when we take enolic form, this proton is added across the H and they change into this equilibrium form. But upon removal of H, if H is removed from the oxygen, it gets converted into keto form, and when H is removed from alkyl group, it gets converted into the enol form. This is known as the acid catalysis. In a similar way, we will see in the base catalysis. Base, when it is treated in the keto form, it removes this proton and gets converted into the anion, and this anion is stabilized through the resonance into the another structure. And when we treat this base with enol, it abstracts the proton from this enol and it forms a intermediate anion, this negative ion. And in the reverse direction, if we add protons and if the proton is added at this carbanion, it is converted into keto form, and proton is if added at oxygen, it is converted into the enol form. This is about the base catalysis. Let us summarize the whole topic. Ethyl acetoacetate exhibits keto-enol tautomerism, and pure ethyl acetoacetate contains 92.5% of the more stable keto form and 7.5% of the less stable enol forms, and both these forms have been isolated and characterized. And the amount of enol form, however, varies with the polarity of solvents. Polar solvents favor keto form, while non-polar solvents favors the enol form. The keto-enol interconversion is catalyzed both by acids as well as bases. Now, in the next lecture, we will study about 1,3-dithiones. That's all. Thank you.